Hello, we are Xi, Hangxiao, and Samra. Today we will present the paper Escra Event-Driven Subsecond Container Resource Allocation. This paper shows a faster way to manage container resources. My name is Xi. I will talk about the background and the main insight. Let's start from the background. We use containers like Docker and Kubernetes a lot today. This help run apps in the cloud. Many containers run on one server. We need to set resource limits for containers. These are mainly CPU and memory limits. Limits create a boundary for each app. This stops apps from interfering with each other. Why set limits? Three reasons here. Isolation, stop one app using all resources, and stability, keep the system stable, and cost control. Cloud cost depends on resources. The main challenge is what are the right limits? Setting the right limits can be difficult. There is a dilemma here. Performance versus cost. If the limits are too low, apps run slowly, CPU is throttling, or container crash because of OOM. This means poor performance. If limits are too high, resources are idle most of the time. This is low utilization. You pay for unused resources. This means wasted money and low efficiency. It's even harder because application needs change often, also known as dynamic workload. Predicting the exact need is difficult. Setting the just right limits is tough. People try to automate setting limits. Tools like Kubernetes VPA and Google Autopilot exist. They look at the past usage. They predict future needs based on the history. They adjust limits automatically. But this tool has limitation. They react slowly. They often work on a multi-level, oh sorry, they work on a minute level scale. They cannot handle fast bursts well. They rely on prediction. Prediction can be wrong. Bad guesses hurt performance or waste resources. Their approach is coarse-grained. They cannot match instant needs precisely. Because of this, people try to allocate extra resource to ensure safety. People still tend to be over-provisioned, and this will lead to resource waste. So, how can we do better? Can we manage resources faster and more accurately? Escra try to give the solution. What is Escra's core insight? Escra makes the fundamental shift. It moves away from the slow prediction. It focuses on the fast reaction. In less than a second, it based directions on real-time events and current matrix, not the history, not the prediction. How does it do this? It gets very precise and timely information. It knows CPU usage and throttling instantly. It also knows about the memory pressure before OOM happens. The key is accessing the real-time data directly from the OS kernel. This avoids delay found in other tools. It allows very fast reaction. So, Escra can react very fast by using kernel data. What capability does this provide? For CPU control, Escra can make precise and fast adjustment. It closely follows the app's instant CPU needs. It doesn't lag behind. For memory management, it offers reactive OOM prevention. If the use of memory spike in short period, Escra can intervene. It can prevent the container from being killed because of OOM. This improves stability. It also improves memory efficiency. What's more, Escra can enable flexible resource sharing. Containers in the same app can share resources dynamically. This works even across different machines. They share a resource pool with a global limit. This enables a more flexible use of resources. So, what is the final outcome of this capability? Escra breaks the trade-off between the performance and efficiency. This is the most significant contribution here. Escra showed that you can achieve both high performance and high efficiency simultaneously. The paper results show Escra leads to increased performance, lower latency, higher throughput, fewer OOM termination, and resources are given just in time when needed. Escra also increased efficiency, much less wasted resource, better resource utilization, and potential cost saving. Why does it work? Because Escra can address resources based on actual real-time needs. It doesn't rely on slow and inaccurate prediction. How does Escra connect to our class topic? For synchronization and global state, the Escra controller tracks the use of resource everywhere. This is like maintaining a global state. It needs synchronization to keep the state updated from many agents. For concurrency control, many containers send updates at once. The controller manages the shared resources. It needs good concurrency control. This ensures safe updates and consistent decision. Understanding this topic helps us understand Escra's challenge in the distributed environment. Now, Hangshao will explain the system architecture and implementation in more detail.
Hello, everyone. I'm going to introduce the architecture of Escra to you. And before we dive into the technical details of this system, let's first come up with a real-world analogy. Let's first think about a smart factory which has workstations, has managers, has control stations, and in our Escra system, we also have similar structures. For example, we have the application developer and watcher, which works as a production planning supervisor, which can actually take into the job orders and determine which workers are arriving, which workers are leaving. And for the kernel hooks, it works as an embedded workstation sensors, which can sense in how the workstation is working, whether it hits the limits, whether it's working properly. And for the agent, it is like an on-site floor supervisor, which can talk to the central control room and also make some direct adjustments to the workstations when needed. And the controller in the Escra is like the central control room of the factory, which basically does globally allocation of resources. And for the resource allocator, it is like the resource efficient analyst or the dispatcher of this factory. It can determine how and when the resources need to be reallocated. And for the CPU and memory, they're just like electricity and raw materials or supplies in the factory. So first, let's talk about the application developer and watcher in detail. The developer, as we've seen in this graph, the number one section, they actually define the app and the resource limits, which was done by reading some configuration files. And with all this information, the system will be able to know how many containers there and how much CPU and memory resources that we have. And then the deployer will send all this information to the controller. So the controller will have a starting budget in mind and also knows how many containers there. And the watcher will keeps an eye on the container events. And whenever a new container is created, the watcher will see that and tells the resource allocator and the controller that there's a new container, so that the Escra's monitoring system will be able to monitor these containers immediately. The next part is the kernel hooks, which is number three section in this graph. For the kernel hooks, they are like the communication bridge between the kernel space and the controller and the resource allocator. So first, it can open a dedicated communication channel between the container and the controller through a TCP kernel socket. So by this means the controller will be able to know the information, like the working log from the container. And the kernel hook's second function is to collect highly detailed usage stats from CPU and memory. With all these detailed stats from CPU and memory, it will be able to know how much CPU the worker node is currently using and how much memory is currently using. And then it will be able for the controller and the resource allocator knows how whether this node needs to be allocated with new resources or need to be reclaimed with resources. The last function these kernel hooks do is to set a special memory hook. It acts like an early warning system for memory crashes. So like whenever a node is approaching the memory limit, it will send an early warning to the controller so that controller and resource allocator will be able to determine uh, how to allocate more resource to this container and possibly save this container to be killed. However, I think this kind of kernel hooks could break uh, could break the compatibility of this system or require repatching in the real world scenarios like our standard cloud environments because it requires us to directly modify code in the kernel space, which is usually hard to do. The next part is the controller. In the section 2 in this graph, here's a more detailed graph about the controller and the resource allocator. The blue part of this graph is the controller. So the controller's main job is to keep track of the containers and including their usage and the status. So whenever the controller gets the informations, it cannot directly make decisions about whether it will reallocate some resources to the container. However, it should first send all this information to the resource allocator. And the resource allocator will make decisions about how and whether it's needed to make the allocations. And then it will send back the decisions to the controller and it will carry out those decisions. So by carrying out those decisions, the controller did some periodically memory reclamation process. Here are more details about the memory reclamation process in the pseudocode format. First, for the controller, if the controller sees for some container I, the memory limit assigned to that container is much greater than the actually used memory for it, plus the safe margin, which is a margin determined by the user. Then we can say that the container is not efficiently use all the memories. Then, so the controller will then update the memory limit to that container. By the new number is calculated by the currently usage of memory plus the safe margin. And the differences between the new allocated memory limit and the old memory limit will be the reclaimed memory. And the reclaimed memory will be sent back to the resource allocator. So the resource allocator will add this new reclaimed memory to the global memory for future use. One shortcoming of this controller system is, I think, a centralized controller, like we mentioned a lot in our course, could cause a single point of failure under heavy workloads. And since it's a key part of this system, if it fails, that means the system will fail. Last part is a resource allocator, which is the number 4 section in this graph. And we can see the resource allocator is actually like the brain or the commander of the system. It decides when to increase or reduce a container CPU and memory allocations. So for the CPU allocations, when the allocator sees that the container is hitting the CPU quota, it will increase its quota for it. And if it sees the container is not maximizing the usage of the quota it has, it will shrink the quota for it. And for the dynamic memory allocation, it's basically the same process. And by doing the dynamic memory allocation, the system will be able to avoid container crashes by some auto memory events, and so that they can save the containers possibly. Here are the pseudocode for this allocation process. So for the dynamic CPU allocation, first the resource allocator will check whether the container was throttled during the last period T. And if it is, then for the next period, we call it T plus one, we will need more CPU allocated to it. And here is how we determine how much CPU will be allocated. We will plus we will based on the current quota, we will plus the average of the container throttles over the last n periods times epsilon times the maximum available CPU limit minus all the unallocated CPU runtime in the system. And here the epsilon is some parameter that can be tuned by the users. And then we will see whether the CPU on the container is not fully used. If the unused quota during the period is greater than gamma, which is another parameter determined by the user, that means the container is not fully used the quota, so that the CPU limit will be revoked. So we will update the quota for this container for the next period by minus kappa times average of the container unused quota over the last n periods. And here the kappa is also another parameter that can be tuned. For the memory allocation, it's just like when the allocator says there is some unused global memory, then we could allocate those memory to the container when container limit. And here the authors always assign a fixed number of memory to the container memory limit every time. So we call it more memory here. And then if there's not enough global memory left, that means we need to reclaim some memories from other containers. So that resource allocator will tell the controller to do that, which is a memory reclamation process, which I introduced before. And if after the reclaim, there's still not enough global memory, that means all the memories are occupied or used or fully used by all the other containers. That means the current container should be killed.
So these were the three main questions asked when evaluating Escra. Can it handle real-world workloads? Can it maintain a high performance while still cutting back on an unused resource to save money? Does it do better or the same as existing approaches like static allocation or autopilot? These were one of the tests performed. This was run under 4 very different traffic patterns, from constant loads to sudden spikes to exponentially varying request rates. 99.9% latency was tracked to see how fast the app responded and how many requests it could handle, and also how much CPU and memory it wasted. Can Escra survive a serverless platform? 2 applications were used in this case: image process, which continuously processes images like in a media backend, and grid search, which runs long-running distributed compute jobs to find the best ML hyperparameters. So the performance from static versus Escra, compared to static, where resource limits are fixed and set generously, Escra reduced latency by 38% and increased throughput by 25%. That means requests were served faster and the app could handle more users. Escra did this while using fewer CPU cores and less memory than the static setup. This plot here shows that performance and efficiency don't have to be a trade-off when you can scale reactively and fine-tune sub-second intervals. Cost. Here we're looking at how much CPU and memory slack was reserved but never used. You can see that Escra stays close to 0, meaning it doesn't hoard unused CPU or memory. For example, in the train ticket app, static allocation left over 2.5 CPU cores just sitting doing nothing, and Escra trimmed that down to just 0.14 cores. Escra dropped memory waste by up to 95%, which is a huge cost saving if you're paying for cloud resources. Autopilot, which is Google's ML-based autoscaler, is smart, but in this case, it proved not to be as fast as Escra, since it updates every 5 minutes, which is fine for predictable workloads, but not when you're working with unforeseen workloads. Escra updates every 100 milliseconds, and as a result, it cut latency by 36% and increased throughput by over 54%. Escra proves to be a whole different speed class in this case. An example of this is if we look at Hipster Shop under both systems, you can see that Autopilot gave it over 1.5 extra CPU cores, and Escra gave it just what it needed, which is 0.12 cores, and it still delivered the same performance. So Escra gives 11 times more efficient CPU usage with no compromise, and this tells us that being reactive, not predictive, is sometimes a smarter bet. These results show that Escra didn't just win in the microservice test, but also thrived in the serverless test. And both OpenWhisk and Escra plus OpenWhisk ran the same batch job, but Escra used 60 fewer vCPUs and saved 7 gigabytes of memory. This is like getting the same job done with half the servers. In the image process test, a new container is launched every 0.8 seconds. But this performed as a stress test for any orchestrator, and Escra handled it without startup delay and no surge in latency. This curve here shows that latency stayed low and stable, and even with more containers, this kind of adaptability is essential in real-time applications. So a recap of the final results. Escra beats both static allocation and autopilot across every metric that matters. Faster responses, higher throughput, and dramatically less slack in both the CPU and memory. In all 32 experiments, Escra experienced 0 OOMs, while autopilot had up to 8 OOMs in a single experiment. So obviously, Escra isn't perfect. There are some limitations. It needs a custom Linux build, which could be a deal breaker for many cloud environments that want to stick to standard OS images. Every container sends telemetry and listens to kernel events. In the paper, cAdvisor memory monitoring consumed up to 85% of a core. So that is a limitation. Also, while Escra performs well across dozens of containers, the paper doesn't fully explore multi-tenant production scale clusters where thousands of containers are managed by many users, which could be a weakness of the paper. Some takeaways and future work. Escra proves that the future of orchestration is event-driven and not prediction-driven. Why guess what an app might need when you can just respond to exactly what it needs instantly? This opens doors for smarter billing, paying for only what you use down to the millisecond. And from an engineering perspective, one huge next step would be to integrate Escra's features into the mainline Linux kernel. Right now, it's running a custom kernel, which limits its adoption. Also, from a research side, Escra mostly evaluates single-tenant apps, but what would happen if a multi-tenant cluster where apps compete for resources? What would happen in that case? Thank you for your time.